So, shall I start?
Okay, yes. Good morning to everyone. This time we are pleased to introduce to our next speaker. She is the PhD Nimisha Vedanti. She is from India, and below I'm going to read a brief summary of her professional career. Nimisha Vedanti received a master TED in exploration geophysics from Banaras Hindu University, India, and PhD degree from Osmania University, India, while working at CSIR National Geophysical Research Institute in India. She held a postdoctoral position at the University of Texas at Austin, USA, and worked as CSIR Roman Research Fellow at the Department of Geoscience, University of Calgary, Canada. She was a visiting scientist in SINTEF Petroleum Research and NTNU Norway under Indo-Norwegian collaboration programs and has short research stay at the King Abdullah University of S&T. Nimisha successfully led to the Indo-Norwegian collaboration projects on seismic monitoring of in situ combustion process in Balod heavy oil field, India, and feasibility assessment of a CO2 EOR process in Ankleshwar Oilfield, India, in collaboration with NTNU, as SINTEF and ONGC and ONGC. Presently, she is in charge of Shadow Seismic Group and CSIR-NGRI and working on the exploration of shale gas and CBM in Gondwana basin of India, sub-basalt imaging, seismic modeling, 4D seismic monitoring, and assessment of CO2 EOR storage potential of key sedimentary basins of India. Nimisha is a recipient of prestigious awards like National Geoscience Award given by the Ministers of Mines Government of India and Young Scientist Award by the Council of Scientific and Industrial Research Government of India too. SEG USA has selected her as the honorary lecturer from South and East Asia Tour 2021. Thank you. At the end of this webinar, we will proceed to the round of question and answer. So you can write in the chat of this transmission. Or last, Mr. Nimisha Vedanti, may you begin your presentation?
Yeah. Thank you. And thank you very much for such a nice introduction. And I start with acknowledging AAPG Peru for organizing this lecture, this webinar. In fact, this is the first time I'm talking to South American audience, and I'm actually excited about it. Is my voice audible? Can you hear me?
Yes, yes,
Okay,
we
yeah.
can.
Okay, because I face some signal loss. Okay, so you can hear me, right? So, okay, so I was just acknowledging AAPG for hosting this webinar. I thank you very much. Now, as you see, the topic of my talk is exploration of coal bed methane in India. And why I chose this topic is this: I thought that I'm going to talk to the petroleum geologist, and coal bed methane in India is now catching up. It's, of course, it is at nascent stage if you compare the research part what is being done by oil and gas industry in India. The coal bed methane is just started a few years back, I would say. The research and the exploration part. I also see that some of the South American countries like Colombia, they also have good coal reserves, and the CBM exploration is also picking up. So probably we are at same stage in both the geographical locations. So in fact, I invite if you have some more suggestions to improve our work, because we have just initiated. And as I was introduced that I work for National Geophysical Research Institute, so I'll take just one moment to show one slide about what is Council of Scientific and Industrial Research. So our institute belongs to one of the network of Council of Scientific and Industrial Research Institutes. We have 37 institutes all over the country. This is the map of India, you see, and then we can say that we have pan India presence, but all the institutes are not in the geoscience stream. You can see there are institutes in biological, chemical, engineering, and other physical sciences. So we are clustered under physical sciences. But among all these 37 laboratories, the NGRI, which is located here in the southern peninsular part of India, we are the only one who are dealing with the geophysics, and we cover pretty much every aspect of the geophysics, right from seismology to exploration to groundwater issues and mineral exploration, all that. Okay, so coming back to the topic, the exploration of coal bed methane in India. This is the outline of my talk, that I will introduce the CBM, what is coal bed methane and where it occurs in the subsurface. Then what is the Indian scenario, present scenario, how the CBM development started in India, what are the prospective basins in India, and then what are the geological complexities of the prospective basins which are posing the challenges for exploration. Now, many people have hesitation for application of seismic prospecting for CBM exploration. That's why I have put a question mark there, that can really seismic prospecting be very useful for CBM exploration? I will show that with some real field examples with the projects what we are dealing with. Of course, the projects are not completed, and the results, I have to hide some of the interpreted seam names and all, but you can still see the results that what we are able to generate from the complex geological setting and from the high resolution seismic data. So as I said that we have just begun this exploration, the seismic exploration for CBM deposits in India. So the way ahead is quite big, and I have listed some of the points for us, that what we are planning to do in futures once we are done with the processing and interpretation of the data. So there are lot many points in the low road ahead, and please feel free to add more if I miss something. So, why CBM is important for India? So, if you see, in general, in last few years, the natural gas was picking up, and it, in fact, the many people of in this pandemic era, many people are betting for the clean energy source like wind and solar. But for India, wind and solar, it will take some time for actual implementation and actual use of wind and solar power to reach to the common people. We are still highly dependent on the fossil fuel, and it's not possible to switch everything immediately. But there is still a search for a low carbon alternative to oil, and CBM being the cleanest fuel other than natural gas is drawing attraction. That's why a lot of interest from the government side and from the industry side is coming in the exploration of CBM. Many experts believe that the proper exploitation of CBM will adjust the energy structure, and that is the best, or I would say the most realistic solution to meet the energy demands of India and for sustainable growth in future. This picture shows that what are the different gas reserves we get in general in geology. So you see, the coal bed methane is the shallowest. The gas occurs in the coal seams, which are not very deep, which are shallow, compared to other unconventional gases. Like here, you see the tight gas reservoir, the shale gas reservoir. In fact, the depth of the conventional gas reservoirs is also deep compared to the coal beds, which are very shallow. And in India, till now, means most of the coal mines are kind of open cast, so you can see the coal beds out like outcrops. But of course, all those coal beds are not important for are not useful for CBM exploration. When we go for CBM, we have to look for the deeper coal deposit in subsurface. But still, compared to any other gas, the CBM occurs at the shallowest depth, and probably that was the reason that till now, whatever CBM exploration has happened in India, in fact, we are producing also, but the seismic or the geophysical exploration has played a negligible role in that. Mostly, it was done on the basis of wells, and lots of wells were drilled in the coal basins, and the CBM was extracted. This is a picture from a coal seam, and you see this is how the coal occurs in subsurface. This is of course an outcrop, not the subsurface picture, but you see that these are the high carbon content coal layers, and this may be thin, this may be thick. The important thing here is the these thin partings, what you see. These are basically the shell partings, we call it, or we can just call it partings also. Uh, in seismic, or when we map the coal seam, apart from mapping the coal seams, we have to map these partings also, because they play an important role when it comes to the extraction of CBM from the coal seams. So you see, these are kind of very horizontal stratified layers with low velocity and low density, the porous rocks. But these shales can be a problem for production. So these partings also should be mapped. The coal seam structure, the continuity of the coal seam in the CBM exploration area, the depth of the coal seams, all should be mapped properly before we go for a CBM exploration. So, as we know that coal bed methane is generated in coal seam due to the thermal or microbiological process, which happens due to the high heat at the greater depths during the coalification process. In earlier days of coal minings, when the mining was happening to extract coal, it was actually a severe safety hazard, and in the beginning of the mining, it was being vented to the atmosphere, means it was not really being used. Now the CBM is extracted by just drilling the wells into the coal seams, and it simply comes out of the pressure. The extraction process of CBM is not that complicated like the extraction of oil from the oil reservoir. Now, when we go for CBM exploration, we look for the deeper seams, because in general, it is assumed that the higher quality of coal occurs at the great depth, and the deeper the seams, the higher the coal quality and higher the coal's gas content. But this is a general assumption. There might be some exceptions to that. Now, there are many countries which are into CBM production, which are producing CBM, but the recognized active players are USA, Canada, Australia, China, and India. We are the fifth largest producer. We are in the fifth rank in CBM exploration, the CBM player. So CBM, coal and CBM are important for India. You can see that India has the fifth largest coal reserves in the world, and most of the coal seams have CBM reserves. Of course, it may be extractable or may not be, but most of the seam will have. So, having the largest coal reserves in the world, we must be having one of the largest CBM reserves also. We are the third largest coal producer. Now, the first coal mine was opened in the 1774 in the colonial age, and since then the coal has been an important part of the energy diagram for India. It provides jobs, and then we can see from the pie chart on the right side that it provides it more than 40% of the energy need of the Indian people. These figures don't, because these figures keep on changing, and this is from the International Energy Agency. Some of the statistical estimates also say that probably will be this coal dependence of Indian energy on the coal is maybe more than 50%. And I'll not be surprised if it increases, because there is lot of work is happening on the clean coal technologies to make it more eco-friendly. So, having realized the importance of coal and CBM, the Geological Survey of India indicated, they carried some survey and they indicated the Gondwana basins of India, where the most of the coal fields, the Indian coal fields are there. They host the high rank coal, and they also have enormous potential for thermogenic methane generation, the CBM. And inspired with that, they did some baseline data collection. But again, I would like to mention here, not the geophysical data acquisition. They were basically the lot of geological work, and they had many boreholes, the scattered information. And they along with the Ministry of Petroleum and Natural Gas and the Coal Ministry, they came up with an estimate for the entire India, which is approximately 91.8 TCF of the CBM reserves. Of course, the state-wise breakup is also given, but we can ignore that. What I want to show here is, though they have estimated around 90 TCF of the CBM reserves in the Gondwana basins of India, till up to 2016, the established CBM reserve was only 9.9 TCF. This figure also may not be fully correct, but you can at least see that it is around 10 or 11% of the estimated reserve. So was the estimate was wrong, and why this value is so low? In fact, not just this, there were some CBM blocks which were given for development, and they did not find much of CBM. So having realized the importance of the continuous information in terms of seismic or geophysical exploration, and a detailed mapping of the coal seams, um, Ministry of Petroleum Natural Gas, along with the Ministry of Coal, has identified 26,000 square kilometer area in the Gondwana Basin for CBM operation. So you can see the large amount of area, the 26,000 square, it's not properly explored for the CBM exploration. So there is lot much to do. Up to May 2016, the contribution of the CBM to the domestic natural gas production was only 1.6%. And up to 2015, there were several issues related to policy and non-availability of technology. So CBM was always at the backstage. But now, with the ministry carving out the area for exclusively for CBM operations, now the exploration is picking up. Here I'm showing the right side figure you see. This shows the peninsular India. The left side map shows the complete map of the India. The Gondwana basins of the peninsular India, which are highlighted in the black ellipse, these are the main basins where the coal and CBM exploration, which are prospective for CBM, and all the other coal fields are major coal fields are lying in these basins. So I am not sure what color you see, but it is like dark pink, all these basins where the names are may not be readable to you, but these are the main Gondwana basins where we are actually looking for the CBM prospects. And the blue circle is the among all this, the Damodar Valley, which is highlighted in this blue circle, is the most prospective area, because it has the highest rank coal, and it is very prospective for CBM, and that's where mostly we are working using we are acquiring data and working in this area for CBM exploration. The left side figure shows all the coal fields of India from where coal is being produced. You can ignore all this text. What I want to show, that major coal basins are here. circle which is highlighted in the right side. And the Damodar Valley basin, the maximum, the good quality coal fields are rated here. So this is the category. It was categorized based upon the quality of coal and their ash content. So the Damodar Valley is the best area for the exploration of coal and CBM. This is a picture. This is the geology of a sub-basin from Damodar Valley, which is called as Raniganj. And if you see this picture, immediately these red lines, they will draw your attention. These all are faults. So you can assume that how much faulted the sub-basin is. The gray lines, if you see, these are the coal seams which are mapped, and the faults are all along the coal seams. Apart from these lot many faults, we can also see the basic and ultra basic intrusives, the green lines. So all these are the geological complexities which are visible, very much visible in the geological map of Raniganj. One more thing I would like to highlight, the green patch here. This is the base of the Gondwana formation. We call it the Lower Gondwana Talcher formation. This is the last formation or the deepest formation of the Gondwana sedimentation. So here you see it is exposed, which means you can assume that how much tectonic activity has been happening in this basin. These many faults, the lowest formation is exposed, so this basin had been tectonically very active. Another stratigraphic slide for an adjacent sub-basin that is called as Jeria in the same Damodar Valley basin. Here you can see the last row. This is the basement, the metamorphic basement. Above the metamorphic basement, we have the lower Gondwana Talchir, which are basically the shale and sandstone formation. These are the oldest Gondwana formation, the lower Gondwana formation. Above that, there is a Barakar, which is coal bearing and very prospective for coal and CBM, the Barakar formations. You see these black lines in the lithology. These are the coal seams, and they occur in the sandstone shale lithology. So sandwiched between this type of lithology. Above that, we have barren measure, which doesn't have coal, and it is being explored mainly for the shale gas exploration. It has mainly the shale. Then the uppermost formation here is the Raniganj, which is also very prospective for coal and CBM. And in fact, whatever CBM right now is is produced by India is from the Raniganj formation in different subbasins of India. Now, this from Raniganj to Talcher, this is my entire zone of interest. This is my reservoir. There is an unconformity, and then this is the underburden, and in my overburden you see there are tertiary sediments, tertiary and lower Jurassic sediments, where we do have dikes and sills. So we do have a complex overburden above all these formations. Another interesting thing is, many times we do not see a contrast between the metamorphic basement and the Talchir formation because of high. It's because of pressure. The rocks are very hard in this Talcher formation. So many times we are not able to see the contrast between Talcher and the basement metamorphic. We are also sometimes not able to see the contacts between these formations, because they do not the seismic properties are not very different. Apart from that, what is happening, that this due to this dikes and sills, lot of attenuation is, lot of scattering is happening. And then the top coal layers, there are some more seams above this also, they are attenuating the seismic waves. So we are not getting proper signal to target the Barakar formation. This is also happening sometimes. So these are the complexities we are facing while acquiring the seismic data, which again I have listed down. As you the from the Raniganj geological map, it was clear that it is kind of fault lots of faults, and it is like fault controlled basin, and the faults. And all the Gondwana sedimentation has occurred during the Precambrian lineament. That's why you see in the previous picture kind of linear structures here. So the sedimentation was happening along the linear structure. All the basic dikes, faults, and the attenuating coal layer are resulting into low signal to noise ratio in the seismic data. There are many faults and the intrusive bodies in the layers which are causing the lateral velocity variation and scattering the seismic energy. Sorry. Presence of coal layers and lots of high velocity sill and dikes, they are also contributing to the attenuation of seismic energy and are also generating the short period multiples. Apart from all these structural geological complexities, there are some elevation issues also. Of course, elevations are not that variable like in the mountain or the hilly areas, but still we have the elevation issue because we are in the river valleys, so there are issues with the elevations. So collectively all that are resulting into a poor quality of seismic image. Now, apart from the structural geological complexities, another problem what I already explained in fact in the stratigraphic slide, that we are not able to detect many formation boundaries. The seismic properties are not that different to be detected. Then there is overriding of older strata because the Gondwana basin has gone through multi-periodic tectonic activities. So the stratification was affected. We have older strata over younger strata. The velocity inversion problem is happening, and that is happening, of course, also due to the presence of deeper coal layers below the shale and sandstone lithology. So all these problems are making interpreters' job very difficult. Another thing is the shale partings, what we I have shown in the coal seam picture, that the thin coal seams and the shale partings are kind of beyond the resolution of the conventional seismic data. So these are the challenges, these are the inherent challenges of the prospect of the area where we are working. Now, now this is what it is about the geology. Now if we think that what is the technical feasibility of CBM, given that okay fine there is a complex geology, but what do we need for a CBM exploration, what do we want to know? So basically when it comes to CBM, the reservoir is the most important part. We look for the coal seams which are at reasonable depth with lateral continuity over a sizable area. So we are not interested in looking for smaller seams which are not continuous, because the production of CBM may not be feasible from those type of seams. The seam should have adequate thickness for the production. So if there is a thick seam at relatively shallower depth, that is more useful than a very thin seam at the depth, at the deeper depth, even though the gas content might be good in that thinner seam. But the adequate thickness is important. The seam should have good gas content. The methane it should have gas content, otherwise it is of no use for CBM development. Besides this, the most important parameter is permeability. The permeability that will govern the flow of gas in the coal formation. So most of these things can be detected by using a seismic prospecting method. And if we are able to handle the noise issues which are coming either due to geology or due to several other reasons, we can in fact generate the permeability map also for the area. So if someone asks that can seismic prospecting be used for CBM exploration, my answer is yes, because the seismic is the only method which can give you a detailed continuous structural information. You can map the entire seam, we can estimate the bury depth. Then we can go ahead with the impedance inversion and computation of Poisson's ratio, or I would say VP by VS ratio, which can give you information of the at least the free gas present in the coal seam. The SWAV is very sensitive to the fluids present in the formation, so it will detect that. Then a new concept is coming, the frequency spectral decomposition. Today, somehow I'm not covering this topic. I will cover the low frequency shadows and how the frequency dependent amplitude analysis we are doing in my SCG honorary lecture. But I can give you a brief on that. That we know that the seismic wave attenuate, the high frequency of the seismic wave attenuates more than the low frequencies of seismic waves. So this is the basic funda, and when it passes through the fluid, the most of the high frequency components will be attenuated. So we should be able to see the difference in the high frequency part and the low frequency part of the signal when there is a fluid present in the formation. And the same concept can be used for detection of gas in the CBM seams also. So these three are pretty much straightforward and simple. The fourth one, the amplitude analysis and AVO to analyze the lithology and then go for further quantitative interpretation, might be a bit challenging given the lithology, given the geology of the basins where we are working is very complex, because the fourth point needs an amplitude preserving processing step, which we may not be able to afford to handle the noise in the seismic data, which is happening due to source, due to lot of anthropogenic activities, and of course due to geology. So here comes the research part, that we have to still look into the amplitude analysis aspect, that how we can go ahead with that. The other than what I discussed about seismic prospecting, I also like to highlight the conventional seismic prospecting is not good. In fact, is not going to help in detecting CBM reservoirs, because the depth is shallow, and we are also interested in detecting very thin partings and very thin seams to have an estimate of the storage capacity, or to have an estimate of the volume of the CBM. We are interested in a detailed mapping of those seams. So the high resolution methodology is required. The high resolution seismic prospecting is required, which can acquire data in the broad frequency bandwidth, both low and high frequency, while eliminating the high frequency noise, which is very challenging job. Another problem what we have, especially with the CBM reservoir, is the coal seams serve both as a source and a reservoir rock for methane, which is not the case with the conventional oil and gas reservoir, where gas and oil occur in different phases, and the source rock is not the reservoir rock. Here, the CBM might be and mostly, in fact, it is in the absorbed state in the coal bed, so we may not see any effect of gas in the coal formations in the coal seams. And apart from doing the structural analysis, the lithological seismic prospecting, that like means the identification of the lithology, is really very, very important in CBM compared to the conventional oil exploration. So we at NGRI, in collaboration with the Coal India, we have taken 2 blocks in the Gondwana subbasins for the CBM exploration, and we have done everything right from the surveying the area, from the processing, and now in fact the processing and interpretation is going on. So it is like some tests that how the seismic can be used. I think most of you know how what is the concept of seismic prospecting. So maybe the left side figure is not really important. Of course, the shale is written, but that can be anything. What I want to show here is this is the generalized stratigraphy of the Ranigan subbasin where we are working, and which is from where the CBM is already being produced. You see the CBM, the target CBM zones are approximately at 1 kilometer depth. And then we have a wonderful overburden where we have different coal seams which are not of that much interest to CBM prospecting. Then we have another Panchet formation, that is okay. But above that, we do have thin traps which are approximately 170-meter thick. So traps, are always a problem for seismic waves. Then we do have tertiary formations which are fine. But above that, we have approximately 40-meter of thick soil. So we have an attenuating overburden. So it, no matter what we do, they are going to attenuate the source waves what we are trying to what we are trying to use for to map the target. And this might happen that our target is not well illuminated. So compared to any other survey in this basin, the design of survey, the use of appropriate seismic source, and the power is very important when we go for either for CBM or even shell, for it is even more difficult. So it's really important to design the survey and design the seismic source so that we can take care of the complex overburden, and thus our target is well illuminated. This is a test case was done in the same basin west for the stratigraphy I have shown. And let me mention here, the source we used here was an explosive and dynamite source. So the circles are highlighting the discontinuities in the continuous strata, which are interpreted by interpreters as the faults in the Raniganj formations. So all these reflectors are from Raniganj formations. Now you see that maybe the Raniganj formation is we are able to see in the stack section, but the highlighted this ellipse you see, this is lot of noise due to overburden, and we are not able to interpret anything over here. Now, if this type of seismic section is given to an interpreter, though we know that maybe these are the Raniganj formation, it becomes difficult for an interpreter to know where to put these faults on the well. So these are the challenges we are still working on, that how do we correct the near surface section so that our deeper sections are improved. And here you see in deeper section also, we were not able to process it properly. Of course, the target was processed properly, but the overburden and the deeper strata are not processed properly. In the adjacent basin, while we were processing the data, we encountered a feeble signature of a shallow basement. So you can see that from this is the depth contour map for the basement. You see it starts right at the 200-meter. So if the basement is coming right at the 200-meter, this area is not at all useful for any kind of exploration, at least in this part. Then the basement is varying up to 1 kilometer or so. So maybe if we go, I don't remember it's a north south or what, but if we go towards this side, if you see my arrow, then probably we can have some prospects here. But you see the data is so noisy that apart from a feeble signature of the dipping shallow basement, we are not able to detect any of the other formations in this area. We also computed the velocity contours for that to understand more the basement, but that's not important here. Now, what I showed the initial that fault results was from a spike source. Now, due to all environment friendly attempts and all, the use of explosives is kind of prohibited in many areas. So we are using now a vibrator, which this is the real vibrator what we have in our group, and it is a very heavy 50,000 pound capacity heavy duty vibrator, which vibrates in the arrow what is shown, and it generates the compressional waves, the P waves. The problem with the Vibrato source is it generates lot of ground roll, and in fact the airwave also what we have seen, and the airwave amplitudes are also very high in the seismic data. The main problem what we are facing with the vibrator is the high surface waves, the ground rolls, and the airwave. So ideally the seismic section, the pre-processed seismic section should look like this, that you are able to see an airwave which is shown as A, then you are able to see the C, which is the ground roll happening due to the ground motion. Then you have these reflected waves like G, Of course, some dead traces will be there, and then the refracted waves which are at the top. So we filter out all this, and we take only the reflected waves for our further analysis. But when we see our data, we don't really we don't really see the star. We don't really see the reflectors. This is kind not the raw data. In fact, it's some kind of pre-processing, some filtering was done, but we don't really see the reflectors, which ideally it should have been. This is the right side panel. Also, is the pre-processed data where you have airwave, ground roll, refraction, reflections, everything. But you see, we don't really see the reflections. So, what is difference you can see in these two sections is the ground roll and air wave are confined to some part of the section, and the reflection and refraction are getting reasonable part of the section, and they are visible. But here it looks like all the ground roll and air wave are masking everything. So this is what is happening due to the use of this vibrosays, and we have to do some experiment to see that how we can avoid the ground roll, which should not mask the signal. And already we are in complex geology. This is the standard processing steps which probably everyone follows. This is only up to the generation of the final seismic stack, not that is the before the migration. What generally we do is the refracted and air waves, we assume that they have distinct dominant phases. So we use the special filters like FK to remove them. But we are very lucky that these filters are not doing, means they are not working efficiently in our data set, and we see lots of residual noises, there are lots of airwave, especially the airwave, still remaining in the section. So another or best alternative is to do the surgical mute, but that's a really the big job to do. And also application of FK filter, sometimes it is avoided when we are planning to go for further amplitude preserving processing. So we were looking for an alternate method, and then we use the morphological based filters, which of course I did not bring more details of these filters, but these are basically like the attributes what we analyze. We define a structural element, and then we from the data itself we define a structural element, and then we try to move that, and we use the calculus to see that how the structures are varying in the data, and if there are some abnormal high and low values which will be adjusted or eliminated. So that's why it works well on the coherent noise like airwave and airwave especially, because it has got a structure in the data. It will be like same in all the same type of structure it will follow in all the shots. So we apply that on the shot gathers, and you see the right side, it has worked quite well. And the final stack what we have generated, it has improved the continuity of the reflector in the right side. You see, has improved by application of the morphological filters. But unfortunately, we are not able to use this for the 3D. We are just doing some test on the 2D lines. So on the entire 3D processing flow, it has not yet been included. Another problem which we face due to the vibrosays is the noisy sweep signal. This is happening mainly due to the non-linearities in the vibrator system. It has nothing to do with the geology or any other thing. Ideally, the sweep signal which vibrosays generate, it is very different from a spike which an explosive source generate. It will be a band limited signal of with so many frequencies. And you see, I think the next figure will be more clear, that we are expecting a sweep to be with a spectrum with an amplitude like this. But when we when we see the recorded sweep which comes out of the vibrator system, there is a large noise. Now if this is correlated with the recorded trace, it will enhance the noise in the seismic. Apart from that, we are also facing problem with the deconvolution, which I did not include here because I thought it is not, it's mainly for the geologists. But what happens because of these problems, the sections what we get, the events are not at the right place, the events are noisy, and then that makes the interpreter's job really really tough. So we have found a solution that we use the frequency domain sweep deconvolution, but that has to be done on the uncorrelated data. So recording an uncorrelated data in the field is very difficult job. So again, we have not done this for the entire 3D. We have done as a test case on some 2D lines. The peaked velocities, given we have these many complexities, the peaked RMS velocities are not coming that smooth as it will be expected. So these velocities, if we use for the stacking the data, the stack data, the time migration doesn't work that well. You can see here that there is a lot of noise in the data. So what we did, that we knew that since the RMS velocity, no matter how much we smooth it and work on that improvement, it is not going to help us. We started with using the geostatistics here, and we do have the sonic logs, and this is the advantage while working on a CBM field, that you do get many wells in the field, and some wells will definitely have the sonic logs. So we made use of the sonic logs, and we picked horizons from the time migrated section, and derived the velocities from the well using the geostatistical methods, and then generated the interval velocity model. Even this is the same, this shows the fold map, and again this is the same, the interval velocity section. I can skip that. Now even after using that, the depth migrated section doesn't look that appealing. Of course the reflectors have become straight and all, and still we are working on the velocities to improve it more. But what worked well is when we did some kind of velocity filtering, and then some improvement on the velocities, and then we inverted the time migrated data, it has generated much better results. And you can see I had to hide the interpretation done here, because this is under still exploration and I cannot show all that. But what you can see, that 7 and 8, these are the two major coal seams which are being which were the targets for the exploration. These are properly detected, and then other thin seams are also detected by simply doing the deterministic inversion. It is not just, I mean, it is not very something very great, but somehow inversion has taken care of all the noises in the data, in the pre-stack data. And then inspired with that, when we use the stochastic inversion, the methodology which was developed by Srivastava and Professor Sen in 2009, we used a part of data to invert that, and we could detect the thin seams, the partings, pinch out. So it improved the resolution of the data to the extent we did not really expect when we look at the time migrated or the depth migrated section. So these are really good results, that yes, even if you are not satisfied with the RMS velocities what you are picking, and you are not able to smooth it, the geostatistics and the stochastic inversion may help you in generating a better picture of the reservoir, and we are able to detect all the seams whatever we wanted to detect with the thin partings. So that was an interesting and I would say unexpected result for us. So we could go ahead and we generated the roof and floor contour maps for the coal seam. In the coal industry, they call it floor and the roof contour map, but the way we call in the oil industry, the top reservoir and the base reservoir. So they call it the roof and the floor. So they wanted to know, any industry would like to know that how the coal seams are varying in the entire area. So this map was created. And when we matched our results with the drilling depths, we are not very off. You see, this is the roof, means the top seam contour map depth, which was obtained after doing the inversion, and the those adjusted sonic lock was used to convert the seismically pegged roof horizons to the depth. And you see, the depth error is not that high in these wells. Maximum error what we have is the -7. Minus means it went up, and plus means it went down from the drilling depth given by well. Now, in the roof we have more error, but in the floor, the base of the coal seam, we have even less error. The maximum error is -4. It's only 4 meter off we are from the depth computed from the well. So that was the upper seam, and then the lower seam. You see, even it has reduced. In one well, we almost matched the drilling depth. So these results are quite exciting. That only we in this well, in many wells, we are just 1 meter off from the drilling depth. So inversion and the application of statistical methods has really given us good control on the seismic data, and we could show that yes, if we can match to the drilling depth, and seismic can be useful. In the floor, again, here you see that the maximum error what we have is 5 meter, and otherwise 1 meter, 2 meter off we are from the drilling depth. So we with and let me tell you, these results are from the deterministic inversion, because that is the only inversion we can do for the entire 3D volume. The stochastic one we have done for few lines, and we are in process to generate similar type of results for the stochastic also, and I'm sure that will be even better than the deterministic one, because the matching was much better in the stochastic inversion. Now, we also know that the ultrasonic velocities of non-outburst coal seam, which means when the gas is not coming out of the coal formation, is more than 1.5 times than that of the gas outburst coal seam. Of course, this is for one special case, this 1.5 times figure has come, but in general also you can assume that when the gas is out from the coal seam, the velocities are going to drop, and this was measured in the lab in the ultrasound, at the ultrasonic frequencies. So we try to link that with the impedance map. We have computed the upper seam with the upper target seam, the roof and floor contour map, the impedance map for that, and you see the low impedance zones in the upper seam, and in the floor of the upper seam also, which means probably there is gas in the formation, because in the same thing we are getting that much variation in the impedance. And this is please note, this is the upper seam, which is at less pressure and less depth. Now when we go to the lower target seam, the roof has got some low impedance anomalies, but the floor did not. So maybe this is due to the pressure. That pressure in the shallow seam is less, so it is showing the gas is coming out of the coal, and then we are getting that signature, and that is happening for the roof also, but that is not happening for the floor of the lower seam. So if we get more confidence on the impedance values, and we also compute the Poisson's ratio, we will be more confident in generating maps like this, where we can mark the zones where gas is present, where gas is not present, and we should also have these contour type of things, which is measured data from the course of the coal from the well, so that we can confirm that yes, the gas, if my impedance map or my BPVS ratio is showing gas, whether it is matching with the well data or not. So something like that we are now planning to do, but we have to develop more confidence on the impedance and on the velocities. So let me admit that till now whatever we had been done, not much research part has been put into that. It is basically we are trying to improve the seismic section, we are trying to improve the velocity so that we have more confidence on the seismic section, what is being generated, and we can interpret it with more confidence. Then we can go ahead with more quantitative analysis, and we can say more about the CBM reservoir. And in fact, we can give the permeability map also. So the road ahead, there are a lot many things to do. As we have, I was shown in the beginning, that 26,000 square kilometer area needs to be explored. So there is a lot of exploration work should be done, and preferably in few lines, I would prefer that we should also do the multi-component, where because there might be free gas in the formation. The survey design is very important given the complex geology of the area, because lot of noise cancellation can happen when we design the survey properly, and we should take care of how to illuminate the targets properly. We need innovative techniques to update the velocity models, because the standard flows are not able to give us the reliable velocity model, and seismic velocities are the most important parameter what we are getting from the apart from depth from the seismic. Then we should also go for the rock physics modeling of the core of the for the coal, which is kind of new in India. Not much work is done. Once we are done with all that, then we can go ahead with the CBM reservoir characterization. And in case of this, the little complex geologies like this, the well logs and geostatistical aspects will play a major role, and that will definitely complement the seismic data. So that is really important to look into the geostatistical part of the geostatistical part. The core analysis is not means, in fact, we don't have any information right now on the core analysis of the coal, but that will be required when we go for a quantitative evaluation, because right now whatever I had been talking, it was all qualitative, but without core analysis it will be difficult to give any quantitative estimation. And the last, I would like to highlight that since there are lots of problem with the seismic attenuation due to the complex overburden and the attenuating layers, the application of deep resistivity sounding along with the seismic can be very useful, because the coal layers are very resistive, and the deep resistivity sounding is not that sensitive to the these type of attenuation what seismic and electromagnetic would face. So I'm showing this one example, not my figure, and I forgot to put one reference also. This was done for a groundwater survey, where resistivity and seismic was jointly done on the same area, and you see that the zone of high resistive formations, where how nicely those are demarcated, and the depth control and the structural control was given by seismic. So this is the same kind of thing can be done for the CBM also, where depth and structure constraint can come from the seismic. However, the resistive coal layers can be constrained jointly by seismic and um, resistive methods. So that's all. In the end, I would like to acknowledge my mentors, Professor Dimri and Professor Minal Sen from University of Texas, my PhD students who are a part of this work. Whatever I have shown, it's not just my work, it's a group work, the entire shallow seismic team, because right from acquisition, processing, interpretation, everything was done by us. So the entire team gets the credit. In fact, I would like to give more credit to two young women working in my group, which who are even in this pandemic situation handling kids and working from home and delivering results. So I really appreciate those girls' efforts. Then Director NGRI for all his support and encouragement. We have used Paradigm software for processing and CGG software for some of the interpretations. So I thank Immersion and CGG for that. And the dataset belongs to Coal India and the SR Oil and Gas Exploration and Production Limited. Thank you. So
Thank you so much, Mr. Nimisha Vedanti. We are very grateful to you for this information, for your time. Uh, And next, I will give a pass to my partner, Nereida Luque, who is the president of the AAPG Peru Chapters, to direct the question and answer part. Nereida, are you here? Are you there?
I'm here, Anderson. Thank you for introducing me. Hi, Nimisha again. Well,
Hi.
now we are going to pass into the question section. Let me
Okay.
find the questions, please. Okay, I have the first one here. Which elements are basically development in partings in coal seam and how parting are formed?
Partings are basically formed at the time of deposition. Like in the slide, I don't know if I have to share again, but if you remember the coal seam I have shown, the partings are basically the shales which are formed by the when the flood deposits the sediments in the peat swamps. So that's how, and then the next coal cycle starts. So in that duration, those shale partings are formed. So, but of course, I'm not the geological expert to explain more than that.
Well, it's okay.
Uh,
We can understand. Okay, the next one is, Madam, why humus coal and semi-bituminous coal consist sulfur and phosphorus, though it belongs to carbonized process?
well, I don't think I can answer this question because I do not. I'm not into the coal geology, so I cannot really. Of course, the coal, this phosphorus and sulfur are. I read sometimes, but I can't answer this question.
Oh, it's okay. Don't worry about that. It's okay. Okay, the next one is simultaneously extraction of coal as well as CBM is possible? Please elaborate.
Uh, y- if I have to say yes or no, then yes. But the problem was the policies, because earlier the different licenses government was issuing for coal and CBM, so it was not possible. But then I think in sometimes after 97 and then recently in 2015 some modification has been done. So now the same operator is allowed to go for coal extraction, and then the same operator can go for a CBM exploration. So yes, it is technically also it is possible.
Great. The next one. I think this is a geological one. Okay. Madam, why Indian coal is basically two types. I mean, Gondwana and the tertiary coal steel, then coal belonging bituminous and anthracite.
Okay, you are asking why these are the two types. So, this is I don't know how the deposition has happened, because that is mainly into again the depositional history of the coal and all the Gondwana formations, all the sediments. But yes, we do have Gondwana coal, which is a good quality coal, and then we do have tertiary coal. But most of the production, if I'm correct, is happening from the Gondwana basins, and that's why we are more focused on the Gondwana basins. And for if you think about the exploration activities in Gondwana basins, maybe it is more like the extent of Gondwana basin is much large if you see in the eastern part of India, and where already the coal, we have good information, geological information on the coal. So it becomes easy to explore the already known area where we know there are good CBM deposits, and that has to do something with the age also. So that might be playing the role, that how they are the geologists are deciding that which one is good and which one is not good. So I think that's what I can answer on that.
Thank you, Nimisha. The next one is, in between Karaharabari and Barakar formation, which coal seam is rich in methane?
What we have studied is the Barakar. We have not yet analyzed any data on the Karbahari formation, but Barakar formation has good amount of coal, and that's what we are trying to estimate the the CBM potential of that formation. So definitely Barakar will be, because it is deep and it has got all the positive, means all the feasibility, it qualifies the feasibility test. So I would go with the Barakar.
Okay,
But yes, I cannot, because I have not worked on that Karhar Bari, so I cannot say that there is no, because the running engine is producing. So I can't really say whether it will not produce CBM.
correct. The next one is coal constitute bands like bitrain, clarane, durane, and fusane consist methane?
I don't know that.
Okay,
Because
don't worry.
again, this is a typical coal geology question, and I'm basically from the seismic side to map the seams, and also I don't know this question.
Yeah, we cannot deep in detail about the geology part because this presentation is mostly for geophysical part. Okay, so don't worry about that. It's okay. The next one is this one. It's about geophysics, I think. I have a question, Madam. Coal seams are very thin, and it's very hard to map thin beds with seismic method, and that too when the velocity contrast is not too much. So in this scenario, what should we do, considering the velocity or impedance contrast is not high?
Yeah, in fact, that's a very good question, and in fact, that's what the problem we are facing. The velocity contrast is not that good, and some of the seams are very thin. So, but main thing what I would like to highlight here, that when it comes to the CPM, we are looking for themes of certain thickness. We are not really looking for very thin seams. So, if the target seams we are able to map, then it's okay. But what we have to see, that the target seam, if we can detect the shell partings, and if it is pinching out, that should be mapped properly. And that's why we are going for the high resolution seismic surveys, not the conventional one, where we are in fact trying to use frequencies up to 200 hertz, so that we do not miss these thin seams. But due to the geological problems, we have to filter out the high frequency data. Now, another option comes to go for a spectral enhancement while doing the processing of the seismic data. So if you want to enhance the resolution of the seismic data, you can go for the any spectral enhancement method, like the basis pursuit inversion, or the very fast simulated annealing, what we have used in our method, which was able to nicely, it has detected even 2 meter thick seam also. So any spectral enhancement method will help you in enhancing the resolution of the data. And you can go for the inversion if you have sonic wells in your area. So that will definitely enhance the resolution of your interpreted section.
Okay, great. The next one I think is also related to geophysics. How we compute Poisson ratio if vibro size only produces P waves? We need S waves as well for computing PPBS ratio and also Poisson ratio.
Okay. Not necessary, because most of the surveys are done by using compressional waves also only. And if you remember that the typical figure what we see in all our masters classes, that how reflection and refraction happens. So whenever a P wave is hitting a boundary, it gets a part of that is getting converted to S wave also. So if you are recording the S wave, then you can directly use S wave also. Otherwise, also you can compute S wave from the P wave. So you don't need to have the S wave source. In fact, the few years back, the use of S wave source was highly encouraged for lot of complex oil in industry problems. But later on, people again started moving back to the converted P waves, because that is what is realistic to handle. The handling S to conversion of several modes will be very complicated. So I would go for the converted S wave.
Great. What's the basement of Talcher Coal Bed?
Okay, it's a metamorphic basement, Archean age.
Okay. The next one is how partition can be mapped with seismic as seismic resolution is not good.
Uh, Seismic resolution is not good in the beginning, but if you do some high resolution processing or any spectral enhancement method, like what we have used here is the very first simulated annealing method, which in fact not just the VFSA, we have used some fractal based well log statistics, which was used to enhance the resolution in the both high and low frequency part of the data, and that's how we could detect the thin partings also. Otherwise it is not possible to detect with the with the conventional seismic. You are right.
Great. The next one. How permeability map can be generated with seismic?
Good question. I was thinking that somebody might ask me.
Yeah.
So, if you are confident with your impedance, you can generate the porosity maps, and many times we can use the porosity to permeability relations. And in fact, nowadays, lot many techniques. In fact, people are using machine learning algorithms also to estimate. But once you have a good control on porosity, you can give a permeability map. But mind it, you may not be able to give the exact permeability value of the layers, but you will be able to give the kind of permeability trend. Where is the low permeability and where is the high permeability? In fact, this type of work we have done in the heavy oil reservoir in for ONGC, where we could generate the permeability map, which was used to interpret the movement of thermal front in that reservoir. So that's possible.
Okay. The next one is what are your views on the newly launched Indian gas exchange?
Can you please repeat the question? Because something
Yeah.
else is displayed here.
Okay, okay.
Okay. Yeah, now
Can
I
you hear
see.
me?
Yeah.
Okay. What
Yeah.
are your views on the newly launched Indian gas exchange?
I don't know about that Indian gas exchange.
Yeah, that was the
I'm
question.
I'm
Okay, it's
sorry.
okay.
I'm sorry. I
Okay.
don't know about
Maybe
that.
if the participant can explain a little bit
Yeah, you
the
have my
question.
mail ID in case you
Yeah,
want to
we
share.
can
So
we
yeah.
can take the question and send it to Nimisha by mail, and she can answer the question later.
And if it is related to any policy, probably I'm not the right person to answer that because I don't come from that side.
Yeah,
So
that's okay, no problem. And let me see if there is any additional question. Okay, here we have another one. What is the type of soil and what percentage is the extraction of wells? I don't know if you know the answer of this one.
can you display the question, please? I
Yeah,
could not.
for sure. What's the type of soil and what is the percentage of the extraction of the wells?
No, because again, this is out of my domain. So
Okay, this
I
is
don't know what. Yeah,
the production part of the field.
yeah.
Essentially.
I
Yeah.
assume.
Okay, don't worry about it. Um, which type of coal is more viable for CBM
Which type? I
of coal?
mean, what we have in India, with of course, means maybe I'm not again the right person to answer that. But what I have studied is basically the high grade coal with like more carbon content, and then lying at the deeper depths are more are better for the exploration of CBM. But if you are asking about the like composition, the sulfur content, the asker content, and all, I'm not the right person to answer that because I don't know about that.
Great, it's okay. The next one is what could be the new research works that you will recommend? Are there new prospects that you will recommend studying in India?
Yes, definitely. Because see, right now we do not know how means there is some very vague estimate of the CBM reserves in India. We do not really know how much do we have and is it sufficient to meet our energy need. So the first thing would be required to go for a detailed geophysical mapping, I would say, because seismic is the only way how you can get the continuous information, no matter how many wells you drill, and that's expensive also. So I would recommend that the entire all the prospective basins which are demarcated by geologists should be surveyed, and then we should look for the new prospects, because extraction of CBM is not that expensive if you compare to the other oil and gas, other hydrocarbons which in India. So I would go for yes new prospects, which I'd recommend for studying.
Okay. I think we have two extra questions. The first one is, as cost of seismic survey and processing is high, also as we go deeper, the resolution is low. Is there any alternate method to map the CBM?
That's what I was discussing in the last slide, that we have to maybe we should try the deep resistivity sounding, because if our power generator in the resistivity sounding is powerful enough, we can go up to a deep 1 to 2 kilometer deep we can go, and then the coal being highly resistive layer, it can be detected. But the detection of just the coal seam is not important for the CBM, as I mentioned in the technical feasibility. We also need to understand that how much gas content it has, and at what depth it is lying. So other than seismic method, the depth constraint provided by other geophysical method is not that reliable, and detection of fluid is weak for other methods, and seismic does a really good job with that if it is processed properly. So it should be I would prefer that there should be a combination, like in the same lines we run the deep resistivity and the seismic, we can go for a joint inversion, and definitely we can come back with the very accurate prospect estimation. That way we can overcome the limitations of the seismic.
Great. Exploration campaigns, I mean drilling, are still being carried out in India.
Yes, still being carried out, especially when it is in CBM. Yes.
Okay. How many cores would you recommend drilling to quantify the coal bed methane?
How many cores?
Core.
Okay, so see, if we get few samples from each formation, that would do. Like if our say the Barakar formation where we were studying, that was approximately 200 meter thick. So if I get some 10 samples or so, that is good enough for me to characterize that reservoir. But
Okay.
that is from one well. If we are taking different wells and the beds are dipping, then maybe. But in any given point location, the 10 samples would be more than enough for a thicker reservoir, like 200 meters or so.
Okay. And the last one.
Okay.
This is, excuse me, my question was whether the percentage of carbon methane exploitation in India is higher than other countries.
If you are asking like how much coal bed methane we are producing compared to other countries, then no, it is not higher than the other countries, because we, for several issues, we did not do, due to several issues, we did not do much on the exploitation part for CBM, the commercial exploitation. But yes, we are producing. In fact, I had some slide, but I think hide it for that how much we are producing and where do we stand in the global map. I had that slide, but I would have shown you, but it's not there. But we are not definitely highest.
Okay. And that's all the questions, Nimisha. And now we want to thank you again for accepting the invitation of the AAPG Peru chapters to participate in this webinar. And also, we should thank you for sharing with us this knowledge, which is uncommon in this part of the world. The presentation was really detailed and really easy to understand for us. Thank you so much, Nimisha. And now we can give you a certification in the name of all the Peru chapters for your excellent presentation. Let me read the certificate. In name of the AAPG Peru chapters, we want to give this recognition for sharing your knowledge and experience in exploration of coal bed methane in India as a distinguished speaker on August 10. And this certificate is signed by the president and vice president of the AAPG Young Professional Peru Chapter, and in name of all the others student chapter of our country. Thank you so much, Nimisha. We hope to have you here again in the future in order to share the rest of the knowledge you have. Thank you so much for your participation. And thank you for all the attendance to this webinar.
Thank you.
Thank you so much. See you the next time.
Yeah. Thank you.
Bye, Nimisha. Thank you so
Bye.
much. Bye, guys. Don't forget to follow us in our social media networks. We are going to have the next webinar on Thursday, I think, with Henry Posamentier. Please don't forget to follow us, and don't forget to participate in this webinar that is also a good webinar to learn more about the seismic, the sequence stratigraphy. Okay, so see you then, guys. Thank you for all. Bye bye.